Thank you everyone for joining me, Mr. Ish here again for this video. If you refer back to a video I've done very recently regarding the rates of change, in which I gave a very elaborate and detailed conceptual conversation regarding the rate of change, I just want to very quickly review some of the items I presented in there. Remember, the rate of change refers to the slope of whatever function we're determining, like the change in y or change in x, the effect of changing one variable in terms of another. The rate of change, a very important bridging concept between precalculus and calculus. Given that in mind, let's quickly review the difference between a secant and a tangent. A secant is a line which is drawn between any 2 points on a curve, and it gives you your average rate of change. Your average rate of change. The tangent is a line which grazes your curve or your function at a specific point and only one point, and it gives you your instantaneous rate of change. The instantaneous rate of change is apparently more important and useful than the average rate of change. So remember, a secant, if this right here represents my point of interest and I want to know what the rate of change is at this specific point, and all you have is a secant, you can draw another point on this curve and then connect the 2 points and calculate an average rate of change, and hopefully that average rate of change will be applicable to the value you're determining here, but most likely it won't, because as you change your points on the curve, you'll see you can draw more and more different secants, and as the secants change, the slopes change and the average rate of change of those individual secant lines change. But that's the benefit of the tangent line. A tangent line would be a specific line going through this point, which is why it would give you your instantaneous rate of change. And the goal is always to use by some manner of technique the tangent line so that you can determine the rate of change at that specific point in time. And in that video regarding the rates of change, I discussed two techniques. One technique was a very broad technique which involved table of values and approximations and limits by working from the right hand side towards your specific point and then working from the left hand side towards your specific point of interest, which was right over here. You could approximate by use of limits what the slope at that specific point would be, what the instant slope or instantaneous rate of change would be at that point. And as a cheat, I showed you the concept of derivatives, which is like a very quick, easy, to-the-point technique for determining instant rate of change. I want to present a third technique over here, which is kind of a mix of the two. The broad limit type of technique and the derivative. It's kind of like a mix of the two techniques, and it is an important technique to learn because this bridging technique is what you will most likely be taught first in your course before you actually proceed to the topic of derivatives. So that technique depends very heavily on functions. That's why I've called this functions rate of change, because this technique I'm going to show you, and I alluded to it in my previous video, and that is going to be the technique which will be the focus of this video. So please pay special attention to this video. As a very quick review, if supposedly I have a function which looks something like this, and I want to determine the rate of change at this point, and this is something I showed you in that previous video very quickly. I showed you in that, and I'm going to show you again because this is a technique I want you to be paying special attention to for this video. If supposedly you have a point, let's call this point over here x, and we move h units away and we come up with another value, and this value you would know to be x plus h, because if you're starting originally with an x, you add h units to it, of course you end up with x plus h. The point of interest is this point right here. This is the point I'm interested in learning the rate of change, right over here at this. Here would be my tangent line. The coordinate over here would of course be x comma y, but what is y? Your y would be f of x. Why would it be f of x? Because when you plug in x into your function, whatever that function may be, you get your y value. Remember, your y value represents your output. So here's my one coordinate pair, x comma f of x. But for this side over here, your coordinate pair is of course x plus h, because x plus h represents your x value. And what's your y value here? It would be f of x plus h. You see this? Now we have two coordinate pairs. X plus h comma f of x plus h. This is my x1, and here's my this is my x2 and y2 values over here. And over here I have x comma f of x. This is my x1 value and y1 value. And we all know what the definition of a slope is. It's y2 minus y1 divided by x2 minus x1, change in y divided by change in x. When you're using 2 points over here, you're of course using a secant line, because if you connect these 2 points over here, you have a secant line. But our goal is always to determine the instant rate of change, and that requires knowing a tangent line. But we use secant lines to help get us closer and closer to that tangent line. If you're using these 2 coordinate points, your slope definition will actually become f of x plus h. Remember, y2 minus y1 divided by x2 minus x1. Look at my x2 is x plus h minus x. When you do x plus h minus x, the x's will cancel out, and you'll end up with, on the bottom, the delta x, change in x, equivalent to h only. So this right over here is perhaps the most important formula you will see in this video right here. And this is the formula we'll be relying on for all the 3 examples I will show you for this bridging technique. So remember this, f of x plus h minus f of x is equal to h. This will give you what you need as a derivative to help you determine the instant rate of change at the point you are interested in. So let's start by the 3 examples. I'm going to draw each one out separately, and then we will work each of those questions separately. Okay, here's the first function. F of x is equal to 1 over 2x. It's a hyperbolic function. If you were to graph it, it would look something like this. A graph of this hyperbolic function, 1 over 2x, you would get something like this. And it's supposedly you are trying to determine the instant rate of change over here at this point, tangent line, and you want to know the value of your rate of change at this specific point of time, and we want to use a technique using the slope formula I've shown you. Well, this is how we will proceed. The steps are rather easy, but you have to pay special attention to the formula and the notation involved. Look at what I'm doing over here. I'm going to write f with a prime. What does this prime mean? It basically means the derivative with respect to x. The derivative of your function with respect to x is equal to limit h as h approaches 0. Now this will all make sense momentarily. Limit as h approaches 0 is going to be f of x plus h. Now you'll see the formula I just showed you in the previous part of this video, minus f of x over h. And I showed you how you get this. Change in y divided by change in x. y2 minus y1 divided by x2 minus x1, which simplify to that h. All we have to do is plug this function into this form. So wherever you have an x over here is where you're going to end up putting these items over here. Now look what happens. I'm going to do, I shouldn't be putting an f over here. I'll do 1 over 2 times x plus h. You see we're on this part right here. When you put 1 over 2x over here, remember this is why you learned the composite functions, f of g of x or g of fx. So you know how to plug one function into the other. I'm plugging this right here. This is being plugged in over here. Okay, so you have 1 over 2 divided by 2 times x plus h. Then you have this minus sign over here. And you have the original function being minus f of x, which is 1 over 2x. And you know all of this is dividing by h. Now all you have to do is basically solve this out algebraically, and we'll plug in the limit. Now this is a part which will require a little bit of space. So I'm going to start erasing some of these things here on the side so I can make that space. I'm going to come over here and I'm going to open this up. On the bottom I'm going to get 1 over 2x plus 2h minus 1 over 2x all over h. So you see that. Now I have to do a common denominator over here. The common denominator of 2x plus 2h and 2x is basically everything, all multiplying with each other. 2x plus 2h all over h. And now we have to do this little fraction algebra here. This first term goes in this 2x times. This second term over here, denominator, goes in all of this 2x plus 2h times, right? 2x plus 2h. But I gotta parenthesize this because I have a minus sign being involved over here. Alright, now we have to actually solve all of this. We're gonna come loop up over here. We're gonna actually solve this right up over here. I'm gonna get a 2x minus 2h. Look what's happening. 2x, I'm opening up the parentheses, 2x minus 2h all over, this h is really over a 1. If you take this cross multiplied, it becomes part of your denominator on the top. You see, I'm going to put an h over here because this h is multiplying as a fraction divide. It flips over as its reciprocal, and you multiply with 2x and 2x plus 2h over here. We're still using this original function, derivative function over here, to determine what the instantaneous rate of change, the factor which will help you determine the instantaneous rate of change. Now look over here, 2x minus 2x cancels out. What are we left with? Minus 2h on the top and all of this on the bottom. But this h right here, since now everything is in a multiplying or divide format, this h can cancel out with this right over here. And you have to pay special attention to this right here, this limit, as h approaches 0. What happens as h approaches 0? Well, wherever we have an h, we can make that h value approach to 0. If this h over here approaches to 0, you end up having 2 times 0, which becomes a 0. This cancels out over here as well too. Simply because the limit as h approaches 0, this 2h will become 0 as well. You don't have an h here on the top because I cancelled out. What do you end up having on the top and on the bottom? On the top we have a minus 2 because that's the only factor remaining. On the bottom we now have a 2x times 2x, which is a 4x squared. But we can simplify this, 2 and 2's, these are even numbers. Our final answer here is a minus 1 over 2x squared. Look at this. If you take this original function 1 over 2x and you were to take a derivative of it, you'll get a minus 1 over 2x squared. This right here is exactly what you need, the derivative with respect to that original function, which will give you your instantaneous rate of change at any point in that curve. If you look at that that hyperbolic graph and you picked out any point on it, like coordinate number x, if you put that coordinate number x, like imagine it has a value of 10, you put that value of 10 over here and you solve this out, minus 1 divided by 2 times 10 squared, whatever value you'll get will be your instantaneous rate of change at that specific value. So this right here, after you plug in your value for x, will give you your instantaneous rate of change for your function. So this right here, as you can see, is our solved answer. I'm not bothering going forward to actually determine the slope because you have to actually put an x value over here. It'll give you your slope. Then you can from there determine the equation of the tangent line. But this right here is the value that'll give you your slope of your tangent line. This right here, minus 1 over 2x squared, represents the factor you will use to determine the slope of your tangent line, which will determine and represent your instantaneous rate of change. So I know this concept is a little complicated, but you can look at it. You start with the original function and you plug in these f of x plus h and f of x into the area of the original function, which is represented by x. You solve it all out into the simplest terms. You try to eliminate the h's where you can, and then you at the very end do this limit. As h approaches 0, you can zero out terms and actually end up with a final answer. We will look at 2 more examples, and I'm going to write those slightly smaller, and I won't put this function here again just for the maybe I might squeeze it on the top, but just for the purpose of saving some space. So let's look at another example so we can get a little more used to this idea. Let's look at this question. F of x is equal to x plus 2 whole square. A parabolic function which is shifted, the vertex is shifted 2 units to the left. Remember x plus h, x minus h, how that works. 2 units to the left, and it's going through the y-intercept, I would say 0, 4. And if supposing at any point on this curve we wanted to determine the instantaneous rate of change, you would have to draw a tangent line. But before you can do that, of course, you have to determine the actual instantaneous rate of change. And we can do that by using this formula we've been talking about. The derivative of x with respect to this original function is the limit as h approaches 0, f of x plus h minus f of x divided by h, which is change in y divided by change in x. All you have to do is plug these x plus h and this x into the original function in this format and solve it out. And it's basically gonna be over here, you'll have where you have x, you're gonna put your x plus h. See, you'll put x plus h, and then you have this 2, you're gonna square it, minus f of x, which is basically x plus 2 whole square, all over h. The difficult part of this whole question will be actually opening this up, because you have 3 terms in this expansion. You know, you have an x plus h plus 2 multiplied by x plus h plus 2, and that can get rather messy. So I'm going to do that over here. When I do it over here, then I can always erase it just so I can put the final answer here. I have an x plus h plus 2 multiplying with an x plus h plus 2. When you can multiply these one by one each term, you'll get an x square, and you'll get an xh plus 2x, then you'll get a xh plus h square plus 2h. Remember, I'm going to write it out neatly over here, and then the last expansion part using this tool, you'll get a 2x plus 2h plus 4. So I'm going to write this out over here, just the expansion of this part with the terms already combined. I have an x square, and that'll stay as an x square. I have an xh and an xh, I'll combine as a 2xh. I have a 2x and a 2x, I'll combine as a 4x. I have a h square, which will stay on its own. And then I have a 2h and a 2h, which will add up to a 4h. And lastly, I have a plus 4. So this right here is this whole term, the first term expanded out. You have to expand it out because that's the only way you'll get to your final factor, which will represent your instantaneous rate of change. Then this part is easy. This is basically an x plus 2 whole square. You're opening it up, but it's going to get hit by this minus sign. You'll get a minus x square minus 4x minus 4, and everything is all divided by h. Now this is actually the easy and the fun part, because this is the part where you get to make something look from being complicated to something easy, and you can do that by cancelling things out. Here you have a positive x square, here you have a minus x square, they cancel out. A plus 4 minus 4, they cancel out. A minus 4x and a plus 4x, they cancel out. Very good. You're only left with few items, and they all happen to have h's in them. This is what you're left with. You have a 2xh plus h square plus 4h over h. Isolate h from your numerator. You get h into 2x plus h plus 4 all divided by h. Cancel these out. What do you get? You get a 2x plus h plus 4. But remember, this is all with limit as h approaches 0. Remember, as h is approaching 0, hopefully the value of that h is becoming 0, and it is. Here you have an h, it will become a 0, so you can 0 it out and remove it. You're essentially just left with a 2x plus 4. This 2x plus 4 represents the factor you will use to determine your slope of that tangent line. If you had an actual coordinate, all you would have to do, like an actual coordinate which lies on that curve, the coordinate of interest where you want to draw your tangent line, all you have to do is plug in this x value right over here, solve this part out, and you'll actually have the slope. This will give you your slope of your tangent line, which will represent your instantaneous rate of change. So you can see how this process is drastically different compared to using the table of values and compared to using the derivative techniques when and if you learn them later on down the road. So this is like an intermediate process. You're using a combination of both techniques over here. You're still using the concept of a secant line, because the secant line concept is what has given you this formula, the change in y or the change in x. You only have a change in y and a change in x because you have two different points which will lead to a secant, and you're using that secant formula to determine the eventual slope of that tangent line. So here your actual answer is 2x plus 4. This will represent your factor from which you can determine the slope of your tangent line. Let's look at one last example, and that will be the end of this video. Let's look at this function here. F of x is equal to square root of 1 minus 2x. If you calculate the 0 of this, 1 minus 2x equals 0, you solve for x, you'll get x is equal to 1 over 2. This right over here represents my 1 over 2 comma 0, and this right here is 1 comma 0. If you were to solve actually for the y-intercept, you will determine that the y-intercept over here, if you 0 out the x, you'll get a square root of 1, and my y-intercept is a 0 comma 1. So this right here is a pretty accurate graph of this function here. If at any point on this graph you wanted to determine the equation of a tangent line, a line which just happens to graze that curve at that one specific point, then you need to be thinking about some technique which will help you determine the instantaneous rate of change for that specific point. So let's show you using this common technique we have been talking about in this video. I will erase this graph over here for the purpose of having space. I'll need space because now in this function I'm dealing with a radical. And when you're dealing with a radical, in that form that we are talking about in this video, things can get a little complicated because you got to start rationalizing the radical. So let's look at this. Our base equation we all know is the derivative of x, the derivative which you're determining with respect to x, is equal to the limit as h will approach 0 of f of x plus h minus f of x, which is always your original function, y2 minus y1, divided by x2 minus x1, which happens to become h. 2 points leading to an equation of a slope of a secant line, but this secant line will help us determine that for a tangent line, the slope. As you know, you have to plug in what you see over here in terms of x, what you see here, and your equation will become this. You can have a square root of 1 minus 2 times x plus h. You see I have an x over here, this x plus h will enter over here. Again, kind of a composite form, composite functions here, one feeding into the other, minus f of x. What's your f of x? It's your original function, 1 minus 2x. The ability to see and what, the ability to see what to plug and how to plug it will only come with practice, because some of these types of functions can get very tricky and you have to know how to plug this into that. All over h. Now look over here, what can we do? Well, the best thing we should do over here is actually create some space, because we might need it, especially when we're dealing with radicals. I'm erasing this top part because by now you might actually have it committed to memory. Look over here on the top. The first thing we want to do is open this part right here so we can see it more clearly, and let's do that. You have 1 minus 2 times x plus h, which is really 1 minus 2x minus 2h. See, 1 minus 2x minus 2h minus this other part, 1 minus 2x, all under radical, all over h. We have to basically rationalize the numerator over here, because if we don't rationalize the numerator, we can never get to our final form. Let's erase this over here and start rationalizing this. We will rationalize the numerator here, not the denominator, in this form. I'm going to repeat what I've written here. 1 minus 2x minus 2h minus 1 minus 2x, this is all over h, multiplied by the rationalizing factor. 1 minus 2x minus 2h. And how to rationalize, I've presented that in another video. You can always pay attention to that rationalizing radicals video. 1 minus 2x. And the procedure for rationalizing is to multiply the radical by its conjugate. If something was minus, you multiply it by the conjugate, which is a plus. And you do the same thing both on the numerator and the denominator. So what do we have over here? It looks complicated, and here, because I'm limited by space, I'm constantly having to erase what I've written, but that's fine. If you had a piece of paper in front of you, you wouldn't have to worry about that. I'm going to multiply the top with the top, and I'm going to multiply the bottom with the bottom. Pay special attention to the laws and the properties of radicals as you multiply them. And that is a subject I presented in another video. I'm going to multiply the top with the top. This first part with this first part. Remember when you multiply conjugates, minus with the pluses, you eliminate the intermediate steps. So you're only left with the easy task of multiplying one term with the corresponding term and another term with the same corresponding term. And that's all. You don't have to worry about any intermediate terms popping up, because so long as everything is similar looking and you're using conjugates, you don't have intermediate terms. I'm going to multiply the single arrow term with a single arrow term. A radical of 1 minus 2x minus 2h multiplied by the same thing will give you exactly the same thing but without a radical. Minus with this plus will give me a minus. I need to parenthesize here because I'm going to be creating an expression. This double arrow radical with a double arrow radical will give you exactly the same thing without the radical. That's the beauty of it. Now the bottom part, don't open this up. No need to open it up. Keep everything in a parenthesized manner. 1 minus 2x minus 2h plus root of 1 minus 2x. Close this parentheses. Now we basically have to simplify the numerator, and this is how it's going to be. I'm going to do these steps in my head. I have a 1 minus 2x minus 2h minus 1 plus a 2x. You see this plus 2x and this minus 2x will cancel out. The plus 2x and the minus 2x cancels out, and this 1 and this minus 1 will cancel out. All you'll get left with at the end is a minus 2h. You can see this positive 1 will cancel with this minus 1. This minus 2x will cancel with this positive 2x. So you're only left with a minus 2h on the top. On the bottom, I have this h, and I have the rest of this. 1 minus 2x minus 2h plus root of 1 minus 2x. Look at this. The h's cancel out because everything is in either a times or divide format. You can cancel them out. Let's look at the whole concept of the limit as h approaches to 0. What happens as h approaches to 0? Any of these terms which have an h will actually become 0. This right here, minus 2h, will approach 0 and become 0. You are actually left with a root of 1 minus 2x plus a root of 1 minus 2x. That's just adding two radicals. If you have two radicals and they're identical, you just add them up. Easy. Your final answer will be this, minus 2 over 2 root 1 minus 2x. Why is this 2 times root of 1 minus 2x? Because I have the same thing adding to the same thing. You're doubling it. Hence this coefficient. But if you take this one step further, you can cancel these out because they're similar terms. And your final answer is a minus 1 square root of 1 minus 2x. This right here is your factor. If you are to plug in an x value over here, it will give you your slope of a tangent line from which you can determine the equation of the tangent line. All we have to really do, make sure, is our answer is indeed right and we haven't made a silly mistake along the way. And let's erase this part over here on the bottom, and I'll do the derivative technique right over here for everyone to see, and it should look something like this. If it does, we're good. And I want to use a derivative technique for doing that. The derivative technique, you don't have to worry about it for right now. I'm just using it to check my answer. I'm going to do the derivative of this original function 1 minus 2x. I'll use something called the chain rule, d over du root u and du dx 1 minus 2x. I'll end up over here with a 1 over 2 root u, and here on the top, I apologize for bad handwriting here, minus 2. I get a minus 2 divided by 2 root u. Minus 2 and a 2 cancel out to give me a minus 1 over root u. And u over here represented my 1 minus 2x. And this is what I'm getting using the derivative technique. So much easier, so much simpler. But yes, these two answers match. So basically this right here represented the factor which will determine your, after you've plugged in the x value of your point of interest, the slope of your tangent line. So keep in mind there are multiple ways of determining rate of change. The easiest being using derivatives directly. The next easiest technique in my opinion is using this formula where you use the limit of h as it approaches 0, f of x plus h minus f of x divided by h. Lastly, then using the table of values to approximate from either the right hand side and the left hand side to come up using trial and error calculations, the actual instantaneous rate of change, that actual slope of the tangent line. I hope this topic was not too tricky or conceptual or too much confusing for you all. If it is, please leave me a comment and we can always go through some more examples. But I appreciate you watching this video. Thank you and have a nice day. Please like, subscribe and share. Have a good day.